yeah, let's get started. So, in this lecture, I've focused a lot on the theory and reasoning behind complexity. So my thoughts are the more fluent understanding, the easier it will be to problem solve, because the easier we can navigate in our heads, effectively. So I've started right from basics, so like what efficiency is, etc. Things that you'll probably already know, but of course it's better to start from basics and then get more and more detailed. Sourcing algorithms might not appear very much because complexity is very large, but yeah, some sourcing algorithms will be used in the slides. So I will be covering efficiency and resources, what complexity actually is, how to use bounds for mathematical formulae, big O, little o, and others. I'll be talking about that weird complexity that Alan was going on about. So, thank you, Shay. I do like the animations too. Methods of finding complexity. So how might we show that certain things have certain complexities apply, and the difference between the complexity of an algorithm and the complexity of a program. So let's begin. Efficiency and resources. So making a program. A program can be made in different ways, and some of these ways might be more efficient than others. That's fairly obvious, but I'm doing a Sonia and starting right from addition and subtraction. And then, for example, by more efficient, we mean there's one or more aspects of the program that we think are better. So this could be time taken, or the decrease in time taken, or the decrease in the amount of memory used, or pretty much anything else that we want to make better. So a resource, what do we mean by a resource? Everything that has an effect on a computer running a program is a resource. So that could be memory space, storage space, even time is a resource. Because if there's no time, then of course, maybe the program might not be able to keep up with other programs, for example. So the program uses time to run. So if it doesn't have enough of time, then of course it won't be able to run. Time itself, even if it's a bit tricky to conceptualize, it is a resource. So time as well is usually the resource we're concerned about in programming. So we could give hardware upgrades for more RAM or more CPUs. We can't really bend space-time. Anyone want to do a team projects idea later? Might sound fun. So we might not know how much of a resource we'll have when we run the program. So we're going to need to reduce the amount of that resource used by the program. And this is how we can use the complexity. So like the maximum amount of a resource that it might use. And am I going a little bit fast, or is this okay? By the way, this is okay. Alright, cool. So different methods use different amounts of resources. Just putting two and two together, there are different methods, and a computer uses resources. So let's use time as a resource. The amount of time that a program takes to run is called its runtime. I'm sure quite a few of you will know that, but once again, I'm starting from basics. So the algorithms that a program contains also have their own runtimes. So a program will contain algorithms. The program itself will have a runtime, but also the algorithms themselves will have their own runtimes. The greater the program's runtime, and the more time the program takes to run, so the lower its efficiency. Let's differentiate a quadratic. Back to low level. Nostalgia at its prime. We'll shed a tear. So 3 of the ways to do this algorithmically could be, it might be fairly easy, but do you guys want to post in the chat what three of the ways to do it could be? Just get this first thing, like I'm asking. Because also it's relatively early, just to make sure everyone's awake. Chain rule, products rule, excellent. And yes, we could expand. Okay, that's pretty good. So that's correct. We could expand and differentiate the polynomial. We could use the chain rule, multiply by power. Yeah, that's expanding. Multiply by power, subtract 1 for power. But yes, three of the ways we could do it: expand and differentiate. We could use the chain rule. We could use the product rule. Yes, there are other ways of doing it. If anyone who suggests finding a reciprocal of dx by dy, I will kill you, I swear. So let's expand and differentiate the polynomial. Let's see how a computer might do this. So we expand it into x squared plus 2x plus 1. And then let's gather the terms. So differentiate x squared, we get 2x, differentiate 2x, we get 2, differentiate 1, we get 0. Of course, and then we sum the terms together. Of course, we ourselves might be able to do x squared, 2x, and 1 all at once in the differentiation, but because they're different terms, a computer might need to do them individually if they're different terms. So even though it is simple, it does take a lot of steps for a computer. So the runtime might be large, making it slightly inefficient. Even though it might be slightly simple to us. Of course, it does depend on how it's coded. But once again, this is like the basic ideas of how methods might differ. So this is one method of differentiating it. Let's use the chain rule now. So let's see how this works. Let's substitute x plus 1 for u, and then we have dy by du and du by dx. So and then multiply them together. The du's cancel out. So we get 2x plus 2 multiplied by 1, which is 2x plus 2. So this method takes slightly fewer steps, so it has a slightly shorter runtime, making it a little bit more efficient. Even though it might seem to us like a little bit more work than expanding and differentiating the polynomial, for a computer it might be a little bit easier. So now they are two methods, so they differ slightly. Let's have a look at the product rule, see if that's any better. So we expand it out into x plus 1, x plus 1. Coincidentally, both things we're multiplying together are x plus 1. So yeah, we can just do this. And then what do? We do u dv by dx plus v du by dx, which results in x plus 1 plus x plus 1, which is 2x plus 2. So what does this method look like? It looks like it takes a lot fewer steps, so it may be the most efficient out of the three. Can anyone see how it might not actually be that efficient, out of interest? What might cause it to be slightly inefficient? Do you want to post in the chats what do you think? So we're performing a differentiation. What memory used? Yeah, possibly. Why might we be using more memory if we're trying to perform a differentiation? And what are we doing in order to perform the differentiation? Try the second line of the calculation. Shall I show you? Okay, here, I'll show you. Oh, some people are talking. Okay. Here, I'll show you. In order to use this method, we'll need to differentiate even more things. So we're trying to perform a differentiation of x plus 1 all squared, but in order to do that, we're performing more differentiations. So how would a computer know that it won't need to use the product rule again? Of course, there may be methods of saying which method we want to use with each differentiation, but using the product rule, we'll need to perform more differentiations. So a computer might need to use the product rule repetitively instead of just doing one, let's say, expansion into a polynomial. Maybe the product rule is a bit inefficient. The total number of terms as well to differentiate here is more than the number of terms to differentiate in the polynomial. So here we have x1, x and 1 in comparison to x squared, 2x and 1. So we have 4 terms here instead of 3 with the polynomial. So this is going a little bit into analysing the algorithm, which we are going to do later in this presentation lecture. I don't think it's officially a lecture, but yeah, in this presentation. But for now, all we need to know is that different methods, we've looked at 3 different methods for this, may have different runtimes. I know you all saw that 4th method. Alright, you know what, if you want to see it, then let's do the 4th. I won't be talking through the 4th method, but yeah, here it is. Let's do it implicitly as well, just for fun and death. I'm not going to be talking through these, don't worry. You can just go back to these if you want to see them. So, let's now talk about complexity. We've talked about efficiency and resources. We now covered that there will be different methods of solving a problem, and they will have different runtimes. Let's talk about how complexity links with that. So, programs and input data. If a program runs using a particular algorithm with no parameters, then the program's runtime will not change, no matter how many times you run it. So anything that could realistically affect it, so processor type, programming language used, maybe number of cores, etc. Anything, I suppose we can say anything external will not affect the runtime. So let's say the program takes some data as an input and it does something with this data. So this time it has some parameters. The input is an array of some sort, so it can hold a variable amount of data. That's a key point. And the program does an operation on each of these pieces of data in the array, and then it doesn't need to return the array. The thing is, the important things are the array has a variable amount of data, and the program does an operation on on each of these pieces of data. So naturally, we'd expect the program to take more time if there's more data in the array. It would be a funny concept to have a notation of 1 over n, then you can just make n really large and it'll be fast. No, that doesn't exist though. If we say that n is equal to the number of items of data in the array, then the runtime of the program should follow some kind of mathematical function of n. So it could be an estimate, or it could be an exact formula. Well, it's unlikely for it to be an exact formula, but it should follow some kind of function, and we should be able to find that function. It should be possible to find that function. So let's talk about the input size, n. So in computation, if the input size of a program is the only thing that affects its runtime, so we ignore number of cores, programming language used, etc., then we want to know what the worst case scenario is. So this is how the input size is arranged to make the runtime the lowest, or in more formal terms, the time complexity the highest for n items of data. If that makes sense. So complexity, we can think of it as kind of the opposite of efficiency. So the higher the efficiency, the lower the complexity, and vice versa. So why do we want to know the worst case scenario? Because we need to anticipate how many resources the program would possibly use. So if there's a lack of resources and it causes the program to crash, if it's possible for the program to crash because of it, then we need to make sure that never happens. If it's possible for it to use too many resources, then that could be a problem. So if we were to take a server, for example, as it says here, maybe if the runtime for client communication is too high, then the client might throw a connection timeout. The server's taking too long, it might have disconnected. So we want to make sure that unhandled errors are never thrown, because that's kind of our aim, even in the worst case scenario. So if the worst case scenario doesn't deplete the time resources we have, then the error should never be thrown. For those of you that don't know what unhandled means, it means not caught by a catch statement. I'm pretty sure. So, is everyone okay with that? I'm pretty sure. Okay. Cool. So now we have a worst case scenario. We want to bound it. So we always take n is an input of the program, a variable input, I should say. However, we could slightly remodel our program, no matter what our program is, to make it take different aspects of something as the inputs. So if you were to take, for example, a factorized polynomial like before, we have x plus 1 all squared, let's say. That could be taken as either the number of bracketed terms, so the number of x plus 1s, or we could take it as the total number of terms, so maybe x and plus and 1, etc. So those are two different ways we might be able to change. We might be able to remodel a program that we have to take different aspects of something as the input. Most aspects of an input correlate as well. So as the number of bracketed terms increases, naturally the total number of terms would increase in this case. And in computation, even though it's not realistic, we consider what happens as our array size becomes very large. Remember what Paul said, Big Tim only cares about big inputs. So we want to model the worst case scenario as a mathematical function or mathematical expression, so that no matter how large the array size becomes, the program's runtime will still be below that of the mathematical function. So this is what we mean by bounding. If we have an upper bound, if the mathematical function is an upper bound for the runtime, then the runtime shouldn't exceed it, which means we know that, okay, if the mathematical function is acceptable, then the runtime should be acceptable. So let's take f of n as n and g of n as n squared. So we're taking f of n as the runtime for an array of size n and g of n as we've estimated a mathematical function. So just as we said in the second paragraph, no matter how large the array size becomes, the program's runtime, f of n, should still be below that of the mathematical function. So we're calling that g of n. So this means that the function g of n will be an upper bound for the program's runtime. So throughout this presentation, I'll be taking g of n as an upper bound or lower bound if later, but I'll be taking it as a bound for the program's runtime f of n. So this upper bound is an acceptable complexity of the function f of n. So f of n and g of n, if g of n is an acceptable upper bound of f of n, then the upper bound is acceptable for the runtime. So let's talk about how we can use these bounds now. Runtime as a function of n. So we're taking the array size as n, the program's runtime as f of n, and the upper bound for the runtime as g of n, just as we did before. So when we run the program, we don't know what n is going to be. However, we can calculate or approximate what f of n is, what the runtime might be, by looking at the program's code. Sometimes in a question, we might be told what f of n is, in which case, it's 3 marks, sometimes. So we need to find g of n. So this means that we need to find some upper bound for f of n. So any function, as we might remember from the lectures, is acceptable for g of n, provided that g of n is greater than or equal to f of n, is always true after n increases beyond a certain natural. So we need g of n to be greater than or equal to f of n. N also can't be negative, because, I mean, negative lines of code, yeah, that's going to be a tricky thing to conceptualize. If g of n is greater than or equal to f of n, then f of n mathematically can't possibly be greater than g of n. So g of n must be an acceptable upper bound because it's, well, greater. So let's take an example. Let's take f of n as 2n and g of n as n squared. So the function n squared is acceptable for g of n if g of n is greater than or equal to f of n is always true after n increases beyond a certain natural. Hang on a second though. Between n equals 0 and n equals 2, the statement is actually false. Would this mean that n squared is unacceptable? What do you guys think? Do you want to post in the chat? Or, I mean, it might be fairly obvious, but yeah, just for more interactivity with the audience. Large values of n, that's right. So, as we said, n squared is acceptable for g of n if g of n is greater than or equal to f of n is always true after n increases beyond a certain natural. So after we say n becomes large, as you say. So in the case here, after n increases beyond 2, the statement g of n is greater than or equal to f of n is true. So after n increases beyond 2, we can say that it becomes large. So there is nowhere between 2 and infinity for which the statement is false. For all n is greater than or equal to 2, g of n is greater than or equal to f of n. So n squared is an upper bound. It is an acceptable. This makes n squared an acceptable function for g of n. So n squared is an acceptable upper bound, as we said, because it's after n becomes large. Now let's do a little bit of rearrangement with the bound. Is the text size okay, by the way? Because there's sometimes quite a lot of text. It's good. All right. So let's say that g of n. If we can say that g of n is greater than or equal to f of n, so g of n is acceptable upper bound, then we can flip around by reversing the inequality and swapping the two sides. If we assume that the inequality is true, then we know that f of n is less than or equal to g of n. So if we make g of n any larger, then of course the inequality is still going to hold. F of n will still be less than or equal to g of n. So if we multiply g of n by a positive constant, let's call it c, then the inequality f of n is less than or equal to c times g of n will still be true because we're making g of n larger, so the inequality should still hold. Of course, if c is less than 1, then that kind of screws it a little bit. So we're assuming c is greater than or equal to 1. So this means that f of n is less than or equal to c times g of n, which can be rearranged by dividing by g of n to f of n over g of n is less than or equal to c. Now, if that makes sense, have you guys heard of wizardry? Bear witness. Let's assume that f of n is less than or equal to g of n is false, so it's not a suitable upper bound. We're going to assume this, but let's also assume that f of n and g of n are the same types of function. So what I mean is maybe polynomials of the same degree, or maybe they're both logs or exponentials, etc. But we're assuming f of n is less than or equal to g of n is false. So that means that there is nowhere from n equals any natural to infinity where for all n f of n is less than or equal to g of n. However, because they're the same types of function, if the coefficient c of g of n is large enough, then for all n, f of n is less than or equal to c times g of n will become true for n equals some natural to infinity, making g of n a suitable upper bound. As I say, this is wizardry. We're starting off with f of n is not less than or equal to g of n, but we just multiply by a constant, so say f of n is less than or equal to c times g of n. So let's say, for example, f of n is equal to 3n squared and g of n is equal to 2n squared. Okay, naturally we might say 2n squared is less than 3n squared, so of course it's not a suitable upper bound. No, turns out we can just multiply by the constant and it'll all be fine. Let's say for c equals 2, we multiply 2n squared by 2, we get 4n squared, and 3n squared is less than 4n squared. So, as I say, it's wizardry, and I will be referencing it later, but yeah, it's just, well, as I say, wizardry. So, we only care about large values of n, as you said before in the chat. The point which n must exceed to make f of n less than or equal to g of n true is some natural, let's call it m. So this m could be anywhere. The only time that such an m would not exist would be if f of n is consistently greater than g of n until n equals infinity. So g of n is supposed to be the upper bound. If f of n is greater than its own upper bound, then of course that bound is not the upper bound. So, and if that continues until n equals infinity, then it's not. Then g of n wouldn't be an acceptable upper bound, which means that such an m would not exist. So if m can exist, hence some value of n exists for which all n is greater than m means f of n is less than or equal to g of n, then g of n would be acceptable as the upper bound. So, as you said, we only care about large values of n. This integer m is what we're using to define small and large values of n. So it's the boundary between what we're calling small and large values of n. This also means that if m can't exist, like in the second paragraph, then theoretically, well, the boundary between small and large n wouldn't exist. So even if n tends to infinity, it should always be small. It's a bit of an interesting theory, but yeah. So if m can't exist, then n should always be small. Let's go to the next one. Right. The logic. It reminds me of the first semester of the legendary Vincent. So let's put it all together into predicates. G of n is an acceptable upper bound for f of n if there exists a natural number m for which, for all values of n that are greater than or equal to m, f of n is always less than or equal to g of n. We can put this into, for all n is greater than or equal to m, f of n is less than or equal to g of n. This is prime nostalgia, predicate logic. So this can also be rearranged to improve g of n by including the constant c. So for all n is greater than or equal to m, we have f of n over g of n is less than or equal to the constant. So we've done the rearrangement before the wizardry to include the constant. And last but not least, because it's predicate, we got to define all of our variables. So we got to define m and we got to define c. Let's state the existence of the natural m and the constant c. There exists m and c such that for all n is greater than or equal to m, f of n over g of n is less than or equal to c. So this is the complete structure for the predicate formula for, what was that the predicate formula for? Let's find out. So we're at big O notation, the moment we've all been waiting for. Let's go. So what actually is big O? We've talked about efficiency and resources. We've talked about complexity and how that all links together. And we've also talked about bounding formulae. So making a mathematical function that can be a suitable upper bound, g of n, So let's see how big O links into this. So big O notation is a way of expressing an acceptable upper bound for a function. So the O, I believe, stands for order. If g of n is an acceptable upper bound for f of n, then f of n is of order g of n. So f of n is big O g of n. To simplify this, f of n is of order g of n if and only if, when n exceeds a certain natural, so when n becomes large, f of n is less than or equal to g of n is always true for all n, for all large n. It might sound strange, but order g is actually a set. It's the set of functions which have g as an acceptable upper bound. So let's say if g of n is equal to n squared, let's say, then n squared would be an acceptable upper bound for log n, for 2n, 3n, root n, etc. All of these would be functions, and that would be elements of the set order g, for example. That's kind of the theory behind that. So it means that if g is an acceptable upper bound for f is any function, then the function f is an element of the set order g, if that makes sense. So does that need to be one specific function? If you were concentrating on the previous slide, you might just about remember reading something about order g being a set or some random shit like that. If you weren't focusing, then you know now. If we take functions, let's say f, g, and h, then if f is of order g, then g must consistently exceed f after some natural, so it must be an upper bound. If g is also of order h, then h consistently exceeds g after some natural. So f is of order g, and g is of order h, let's say. So these two mean that h is an upper bound for g, and g is an upper bound for f. So you might be able to visualize that in your heads graphically, or maybe mathematically, if you have a very mathematical head mind. So each of these upper bounds should have their own natural number m, which n exceeds to become large. So we can take them as, let's say, mg and mh. So let's say mg is for the bound g, and mh is for the bound h. So we can say if f is of order g, then n must exceed mg, and if g is of order h, then we can say n must exceed mh, for example. That's just how we can use them. Excuse me. So this means that after n exceeds the greater of these two naturals, mg and mh, f must be less than or equal to g, which must be less than or equal to h, which also means, using the inequality, that f must be less than or equal to h. So if n has only exceeded one of the two naturals, then of course the inequality might not hold. But of course, if we're saying f is less than or equal to h, then that should have its own value of m. So its own value of the boundary between small and large values of n. So we can shift that as great as we want up to infinity, and it'll still be greater than mg and mh, if that makes sense. It's a little bit, maybe a little bit tricky to visualize, but effectively, after n has exceeded the greater of the two naturals, then these inequalities should hold. So hence, f is of order h, as well as f is of order g. So therefore, for a function f, if f is of order g, then f is also of order any function that is, for n is greater than or equal to some kind of natural, always greater than g. So from this we can say that the O notation does not need to be one specific function. It doesn't need to be one specific function. Graphically it might seem a bit logically obvious, but here's some proof that we can use. So in saying f is of order g, g is of order h, then we can simplify using using the inequalities and the bounds of n. So this means that anything h, let's say, greater than f means that f is of order h. So this logic means that the upper bound for f, which let's say that's g, could also be anything greater than g. Multiplying g by a positive constant, like if you remember the wizardry with like constant before, doesn't change how f is smaller than or equal to g. So the statement f is less than or equal to cg is also true, because the inequality is unchanged, g is just being made larger. What if cg itself is just another function? So let's say h is equal to cg, for example. This would mean if f is less than or equal to cg, then, well, cg is just equal to h, so f is less than or equal to h, we can say. So not only coefficients, but all we're doing is making g larger by replacing it with h. So anything that could increase g could be applied here. So let's say if h is equal to g squared instead of c times g, then still f is less than or equal to g and f is less than or equal to h, for example. So this shows that g doesn't necessarily need to be the exact upper bound for f. Instead, g should be seen as more of a boundary that f doesn't exceed after a certain natural. So this might sound a bit well, either obvious or confusing, I can't tell. But yeah, it should be seen as more of a boundary that it doesn't exceed. So if this boundary is always very far from f, then there's likely to be a more accurate boundary closer to f. So when the boundary is very close to f and it might have a similar shape, then it's likely to be what we call, or what I call, I don't know the official term, but the optimum boundary. So if we were to take maybe f of n is equal to n squared, let's say, and g of n is equal to n cubed, then n cubed might be quite far from n squared. So so of course it would be an acceptable upper bound, but if we decrease g to n squared, then n squared is still an acceptable upper bound for n squared. In fact, they're equal. So so n cubed might not be an optimal boundary, but it's still acceptable. Whereas n squared may be an optimal boundary, and it's still acceptable. Here's something interesting. Using the idea of optimum boundaries, if f can be any function, and f is of order g, and g is of order h, so that means f is of order h too, can we deduce that order g is a subset of order h? What do you guys think? Should I give you some time to think? I'll leave this up for a minute. So they're both sets. We have f is of order g, and g is of order h, which means using the inequalities, f is less than g is less than h. We can say f is of order h. So does this mean that order g is a subset of order h? Okay, then Okay, let me reveal one point to it. So, using the idea of, should I go back? The constant c, possibly. We can use this point. Okay, no worries. So, using the idea of optimum boundaries, because G is of order H, G will be more optimal, closer to F than H. Well, it might also be equally optimal, because for example, n squared is of order n squared, so they could be equal and still in sets. So G will be more optimal or equally as optimal as H. So if F can be any function, surely order G as a subset of order H would be true. But hang on, the bounding functions G and H might have different values of m for the difference between small and large n. So if we were to say, for example, there could exist functions in order H and not in order G for n is greater than or equal to mh, while n is less than or equal to mg, so if mg is greater than mh, surely order G as a subset of order H would be false. What do you guys? You can just choose a higher m. That's exactly right. The value of m does not matter in O notation. The only thing that matters is whether or not each bound has some m that can possibly exist. So as you say, you can just choose the higher m. Even if mg is greater than or equal to mh, they both exist, and that's all that matters. In the big O predicate formula, all it said was there exists a constant and there exists a natural m. It doesn't say anything about what values they are. All that matters is if they exist. So this means I haven't proven it, but theoretically, order G being a subset of order H should be true. So if this does turn up in an exam question, then yay, you can just look at this slide and you're prepared. So it might still be a little bit tricky to visualize, but the subset should be true. So P, NP, and X, how do these link in? I'm not going to go on and on about these because these probably belong in a different lecture or different presentation. Most of the time, we like to acquire an optimal boundary for big O so that we can refine our program. So that we can know more accurately, what the bounds might be. However, if nothing else relies on the program, and we just want to know if the program can run and terminate in an amount of time, then we might not need an optimal boundary. So we might still, of course, have a large amount of data in the input array, so we'll need to know whether the program takes a small or large amount of time. So whether it's considered fast or slow. This lecture covers both TOC and DSA. I've tried to make it exhaustive for them. So what was that? Yeah, third paragraph. P, NP, and X are sets that contain programs. So if P is the set of programs that terminate with the runtime complexity of O n to the k, so polynomial, and exp is the set of programs that terminate with a runtime complexity of O to the n to the k. How dare someone thumbs down there, honestly. So exp is exponential, 2 to the n to the k. Everything in P is in NP, and everything in NP is in exp. So P is a subset of NP, which is a subset of exp. I'm not gonna bring up the £1,000,000 question. So programs in P terminate in polynomial time or polytime. Programs in NP terminate in non-deterministic polytime. NP probably belongs in a different lecture, possibly in Turing machines or P and NP. Those lectures, whoever's hosting, P. I'll tell you after I've submitted mine to try and get £1 million. But whoever's going to host Turing Machines and PNP, I'm sure your presentations will be absolutely legendary. But P, NP, and X probably belongs in your lectures, presentations. Victor, yeah, you better prove it in your lecture. So, sorry, Victor, you're gonna have to. So, wizardry. Do you guys remember that wizardry? Remember that shit about the constant C? Remember the wizardry? Constant C? Sometimes it makes sense, but sometimes it's just wizardry. Why should it make sense? Remember all that confusing shit about F being less than or being greater than or equal to G. So G is not suitable upper bound. But if F and G are the same type of function, then there exists a constant which we can just multiply G by to make the inequality true. No, F is greater than or equal to G. Why should we just multiply it by a constant? So in that case, even if G isn't a suitable upper bound for F, and they're the same type of function, we can just multiply G by a constant. Everything is fucking fine, even though G is smaller than F. What? The constant is used in big O. It makes no sense. Why the hell should we have a constant? We do not need this mathematical corruption. If G is less than F, then it's not a suitable upper bound. It should not be a suitable upper bound. Screw C. Screw the language C too. C? No. And I welcome little o notation. Yeah, C just shattered. So let's go for little o. So how is little o different from big O? I should have done that lowercase. Oh, it is lowercase o actually. The constant. The bloody constant. That's pretty much it. Can we define little o? Yeah, C. Why do we need the constant? Little o is better than big O because it doesn't include the constant. So big O is defined by saying there exists a natural m and a constant c such that, well, we've seen the predicate formula before. There exists an n and a c such that for all n is greater than or equal to m, fn of g of n is less than or equal to c. If we were to simply ignore the constant, then we could just say for all n is greater than or equal to m, f of n is less than or equal to g of n. Actually, little o is stricter than this. What we need in order for f to be of order of little o g is for the simplest form of f of n over g of n to have at least one term that includes n in the denominator. So that sounds a little bit difficult, but there is a method that we'll look at in a few slides that can help us decide whether f is of little order g or not. So even if it sounds a little bit tricky to conceptualize, we'll look at the method in a couple of slides. Yes, that is correct. That's the method that we're going to use. So we're still ignoring the constant, but some of the methods that we can use for big O we can't use for little o. So for definition of little o, we're going to need to use something other than predicate logic, which is limits, as Shay puts it in the chat. So for limits, we're going to need to know about convergence. If you've done further maths, you'll probably know about convergence, or maybe in normal maths at A level. So convergence is what a function does as its variable approaches a value. So for a function f of x, we say that f of x converges to, let's say, a as x approaches or tends to b, where a and b are values. So we say that the variable, as the variable tends to a value, the function converges to a value. So let's say imagine f of x is 2 plus 1 of x, for example. As x tends to 0, so as the variable tends to 0, f of x, the function, converges to infinity. So because 2 plus 1 over 0 well, 1 over 0 is infinity, so f of x converges to infinity. And likewise, as x tends to infinity, f of x converges to 2, because 1 over infinity is 0. There's a method of calculating convergence called a limit, as was mentioned in the chat. The limit is the value that x tends towards. In the example of f of x is 2 plus 1 over x, we can say the limit as x tends to infinity of f of x is equal to 2 plus 0, which is 2. This means the limit of f of x, as x tends towards infinity, is 2. We can substitute 1 over x for 0 because 1 over infinity is equal to 0. Considering the natural m which n exceeds to become large, if m exists, then infinity will always be greater than m. So this means as n tends to infinity, n will be large because it will always be greater than m. So we can use this to consider what happens to f of n over g of n as n tends to infinity. So what actually happens as n tends to infinity? There are 3 possibilities. So let's say the function u is n squared and the function v is n cubed. So what's one of the 3 possibilities? One possibility is f of n over g of n converges to infinity. So f of n will be greater than g of n at some point beyond any natural n. In this case, there is no constant c that satisfies f of n over g of n is less than or equal to c, which means it's not of big order g. So let's take an example for f equals v at the top and g equals u at the top. So f is equal to n cubed and g is equal to n squared. The limit as n approaches infinity of f of n over g of n is the limit as n approaches infinity of n cubed over n squared, which is n. So as n tends to infinity, then f of n over g of n will tend to infinity. Infinity is greater than any constant c, so of course it can't be a big order g. Another possibility, so that was one possibility, another one is that f of n over g of n converges to 0, hence g of n is greater than f of n at all points beyond some natural m. In this case, c can take any value, so theoretically it could even be 0. To satisfy f of n over g of n is less than or equal to c. So f is of big order g. This also usually means g is quite far from f, so it might not be the optimum boundary. So let's say for f is equal to u and g is equal to v, as we have at the top, and then f of n over g of n will be equal to n squared over n cubed, which is equal to 1 over n. So the limit as n approaches infinity of 1 over n is 1 over infinity, which is 0, for example. So what's the third scenario? The third scenario is that it converges to a real constant. So g of n is equivalent in size to f of n, if that makes sense. This might not mean that g of n is greater than f of n. However, using the wizardry, big O notation, the constant c can just become large enough to satisfy the inequality. The bloody wizardry, honestly. So f is of big order g. This also usually means that g is the optimum boundary. So let's take, for example, f is equal to 2u, so 2n squared, and g is equal to u, so just n squared. Then f of n over g of n is equal to 2. So the limiting factor limiting factor is just another way of saying limit. So the limit as n approaches infinity of 2 is 2, so it's just a constant. That's the third scenario. So 3 scenarios, just to summarize: f of n over g of n as the limit as n tends to infinity could be infinity, 0, or a constant. Those are the 3 scenarios. The wizardry, that's just an example at the bottom. For f equals 500,000 u and g equals u, we can just set the constant c greater than 500,000. It's relatively stupid. This is why I prefer little o over big O. So now, we couldn't define little o using predicates. Of course, it's already been defined in the chat, but I'm going to do it here anyway. Let's define the little bastard. Little o can't run forever from us. Convergence to infinity is what we'll use to define it. So 3 possibilities. If anyone was listening on or concentrating on the previous slide, do you want to quickly post what they are in the chat, or should I just reveal them here? 0, infinity, or constant. Excellent. So it converges to infinity. So f is not of big order g. It converges to a constant. So f is of order g, and g is the optimum boundary. Or it converges to 0. So f is of order g, and g is not the optimum boundary. And these 3 you said in the chat. Nice. So the difference between big O and little o is, in the second case, where it's a constant, f is of big order g, but f is not of little order g. So this is how little o is stricter than big O. F will be of little order g only if f of n over g of n converges to 0. It can't be any constant, unlike big O, it must be 0. This is what we mean by screw the bloody constant. So, a definition, as we said, f is of little order g only if the limit, as n approaches infinity, of f of n over g of n is equal to 0. Yeah, Shay in the chat, x is meant to be equal to n, but you know what. Yes, if no, that's fine. It could just be substituted for x. But as you said in the chat, that is correct. If f is of little order g, that implies f is of big order g. So also, we can actually define big O in the same way. So we can define big O in predicate, but we can also define it in terms of infinity limits. So f is a big order g only if the limit is at n tends to infinity of f n of g of n is in the positive reals, including 0. Yes, I still believe 0 is not real and yet still rational, but yes, so big O can actually be defined in terms of infinity limits too. So this also means that f is of little order g only if f is of big order g and g is not the optimum upper bound. R plus 0, that's positive reals including 0. I don't know if that's the proper notation, but it's the same with integers. So z plus 0 is positive integers including 0. So I use the same for reals. So now we've done big O, we've done little o. There's a few more complexities. Let's have a look at them. Omega. So big O and little o are different methods of denoting an upper bound for the worst case complexity of a program. So they're both upper bounds, but little o is a little bit stricter. Omega is a method of denoting a lower bound instead. It's still for the worst case complexity, but it's a lower bound. So imagine functions f and g. If f never exceeds g after n exceeds some natural m g, then g is an upper bound. Similarly, for a function h, if h never exceeds f after some natural mh, then h would be a lower bound. So if g is an upper bound and h is a lower bound, then f never exceeds g, but h never exceeds f. So f is bounded by, well, the upper bound g and the lower bound h, you can say, if that makes sense. So big O, we have the definition here. There exists an m and a c such that for all n is greater than or equal to m, f of n over g of n is less than or equal to c. Similarly, omega is defined by there exists an m and a c such that for all n is greater than or equal to m, fn of g of n is greater than or equal to c. So the only difference between omega and big O is that fn over g of n must be greater or equal to c instead of smaller or equal to c. In terms of infinity limits, omega is the reverse of big O. So we have the three. So we have three possibilities. It converges to fn over g of n converges to infinity. So f is not of big O to g, but it's of omega g, and g is not the optimal lower bound. Just like the reverse might say. If it converges to a constant, f is of big order g and f is of omega g, and g is both the optimum upper and lower bounds. So omega still has optimum bounds. And then, just like the reverse of big O would be, if it converges to 0, f is of big order g and f is not of omega g, and g is not the optimum in the upper bound. So as we can see, omega and big O are kind of flipped in these scenarios. They're almost mirrored in a way. That's a relatively good way of remembering it. So almost everything about omega is the reverse of big O, but the mechanics of it are the same, because it's still measuring the worst case complexity, for example. And the theory about the sets of orders still applies to the sets of omegas, for example. So just like with big O, if g is of omega h, then omega g is a subset of omega h, for example. That's an example of how some of the mechanics might be the same instead of mirrored. Visualizing it logically is usually the way to do it. But one of the most important points is that scenarios for order g is mirrored for omega g in three convergence scenarios. So we've done big O, little o, and omega. Let's do theta. Theta is a way of attempting to locate an optimum upper and lower bound for a function f. So if theta attempts to denote both an upper and a lower bound for f, then surely it takes two functions, so maybe big O and theta for the upper and lower bounds. So for example, maybe we could use some big O function for the upper bound and some omega function for the lower. Is this correct? If you guys remember in the lecture. Actually, I don't know if Alan talks about whether they have two different functions. But I will reveal it here. Aye, someone's typing. Scalar multiple. Yes, that's what the constants do. But are they actually? But could they actually be different functions? I'll let you guys type. Being of the same order. So okay, yeah, you're correct. So they need to be of the same order. It does not take two functions. This is a common misinterpretation. Yeah, yes, what you posted in the chat is correct. So the theory about using big O and omega to denote two bounds is correct. However, we're attempting to locate the optimum bounds. Yes, it uses two constants, as you said in the chat. So remember the three convergence scenarios for f of n over g of n. In the case where fn over g of n converges to a constant, g was both the optimum upper and lower bounds. And so because theta attempts to locate the optimum upper and lower bounds, we have f is of theta g only if fn over g of n converges to a constant and not equal to 0. So of three scenarios, three convergence scenarios, infinity, a constant, or 0, it must converge to a constant not equal to 0. So the upper and lower bounds will have the same function, big O and omega. Theta takes only this one function, not two functions. So as you said, it can be defined in predicates. I think it can also be defined in terms of infinity limits, but this is how to do it in predicates. There exists a natural m and constant c1 and c2 such that for all n is greater than or equal to m, c1 times g of n is less than or equal to f of n is less than or equal to c2 times g of n, just as you said in the chat. Excellent. So we have done big O, little o, omega and theta. Tilde notation. This is an interesting one. So we have tilde is a way of attempting to locate a stricter upper and lower bound than theta. It has the same relationship to theta as little o has to big O. Screw the constants and set m to infinity. A fancy name for f tilde g is that f and g are asymptotically equal. Asymptotically? I'm not quite sure how to pronounce it. But yeah, is that they're asymptotically equal. So at the horizontal asymptotes, so we say that's that's n equals infinity. Two functions f and g must be equal. So this means the limit as n tends to infinity of f of n over g of n must be equal to 1. So because you can only have a fraction equal to 1 if the numerator is equal to the denominator. So if f of n and g of n are equal, then the fraction should be 1. And because if they're asymptotically equal, then as n tends to infinity, the horizontal asymptotes, the fraction should be equal to 1. So if g is the optimum upper and lower bounds for f, so in the three scenarios, infinity, 0, constant, then f of n over g of n converges to a constant, then as n approaches infinity, it still doesn't guarantee that f is of tilde g. So it does mean that f is of theta g, as we saw in the previous slide, but it doesn't guarantee that f is of tilde g because it's slightly stricter. In order for f to be of tilde g, the constant c must be equal to 1 because f of n must be equal to g of n as n tends towards infinity, asymptotically equal. So logically, okay, can everyone hear me? Okay, you guys can hear me. Let's see. Should we wait for Ollie? Or yeah, I know. Most people can hear me. Okay, I'm going to carry on till because most people can hear me. So fifth paragraph. Logically, despite little o being stricter than big O, there exists no functions f and g such that f is of little order g and f is of tilde g. So little order, little o and tilde are the two stricter ones, but there should exist, theoretically exist no functions f and g such that f is of little order g and f is of tilde g, because f being of tilde g, it will be of tilde g only if g is the optimum bound for f, so the limit converges to a constant, and f and g have equal leading coefficients, which means that their constant will be 1. So leading coefficients, I don't know if that is the proper term, but for example, let's say in a polynomial, we know that let's say a polynomial of degree 3, we know that the most significant term will be the one with x cubed or n cubed. So leading coefficients is what I call the coefficients of the most significant term. So for example, the x cubed in a polynomial of order 3, because that's the only one that will matter for the limit as x tends to infinity or n tends to infinity. So f will be of tilde g only if g is the optimum bound for f and f and g have equal leading coefficients. Whereas If g is the optimum bound for f at all, then, well, it converges to a constant, not 0, because f is not of little order g. Wait, hang on. Yeah. So tilde is defined by fn will be of tilde fn will be of tilde g and g of n only if the limit as n tends to infinity of fn of g of n is equal to 1. This also shows that this also shows that f being of tilde g implies f is not of little order g and vice versa, since little o uses the same equation, the limit as n tends to infinity of fn of g of n, but results in 0 instead of 1. So, of course, naturally, you can't have both f being of tilde g and f being of little order g. It's just an interesting concept. So we have little o, which is a stricter big O. Big O? Nah, screw the constants. Little o. We have tilde, which is a stricter theta. So nah, screw the constants. Let's go to tilde. And omega, when we make it stricter, does this actually exist? Yeah, I don't think we learned about stricter omega. If one does exist, then my apologies, but I don't think one exists. There's still one left. There is one complexity measure that I haven't mentioned yet. Please, try not to die when you see it. It will likely give you flashbacks. The bewilderment, the confusion, the hurricane, the complicated complexity, clashing in our cognition, causing our crania to collapse and cry for our causes to be recreated without this catastrophe that our cortexes need to comprehend, this apocalyptic calamity of chaotic topics. Amortized complexity. Apologies, I like to put a little bit of entertainment in my slides. We will dive deep into hell. So, is this yet another notation? Amortized complexity, yes, I used the correct spelling, or as some people call it, the British spelling, I did not spell it with a Z, is not actually another notation. It's a different kind of measure of complexity to what we're used to, but it still uses the notations that we've learned about, so big O, little o, theta, etc. So when we're given a program, we can find the runtime complexity of any of the program's algorithms, which we give as a complexity notation of the input size n. So big O n squared, omega 2 to the n, theta log n, etc. We've usually calculated a complexity of a single run of an algorithm or program with an input size of n, and we've assumed nothing changes the runtime except from the input size. So the runtime should not change no matter how many times the program runs, provided the input size remains constant. So of course we're ignoring like the number of cores, the programming language we're using, etc. So what's the difference between amortized and normal complexities? An algorithm operates on each piece of data in the array that it takes as its parameter, causing the algorithm to use an amount of runtime per operation. So maybe for every element in the input array, it might operate on each of these, which uses a little bit of its runtime. So the normal runtime complexity is the complexity notation, big O, theta, omega, etc. of its runtime as a function of its input size n. So maybe a big order, a bit big O of a function. The amortized runtime complexity of the algorithm is just as with the normal runtime complexity, the complexity notation of its runtime as a function of, instead of the input size, the number of times the algorithm runs. So that's the key difference. So before, we've assumed that the number of times that the algorithm runs doesn't affect complexity, So in this case, the amortized complexity would be equal to the normal complexity. In the case that the program might change slightly between consecutive runs, the complexity can be amortized to almost average it out in a way. So it is not actually an average. It kind of averages out the complexity across several runs. So when might the algorithm change slightly or be different between runs? So let's take the current algorithm run as I. So we've run the algorithm I times, let's say. So just like in a for loop, we might use I. Theoretically, if let's say there exists a mathematical set U such that when I is an element of U, something else might happen in the algorithm. So then the algorithm will be slightly different between runs where I is and isn't in the set U. So this is just a mathematical way of saying the program might behave differently on certain runs. So one of the examples we looked at in a lecture was inserting into a dynamic array. So a dynamic array can increase in size when it's full. So so we say that the array grows every time the array becomes full. In this case, the set U contains the numbers of insertions that would cause the size of the array to increase. So the set U, when on the run I, when I is contained in the set U, we might cause the array to grow as well as an insertion. So which would cause the algorithm to be slightly different from just an insertion. So on runs where I is not in the set U, we just perform an insertion. On runs where I is in the set U, we perform an insertion and an array growth. So the algorithm has changed slightly because we're doing more than performing just an insertion. So this is an example of how the set can be used. So calculating amortized complexities, how might we calculate it? Let's have a look. On certain runs, the algorithm might be slightly different or have additional commands. So like before, the additional command might be growing the array instead of just inserting. The amortized complexity of one algorithm run is the average cost of a number of runs per single run when no additional commands might occur. This might sound very confusing. It might be a bit tricky to visualize, so I'll run through the dynamic array example. So the dynamic array example that I believe we did in a lecture. So in the algorithm there exists the base command and additional commands. So the base command is the command that the algorithm runs when I is not in the set U, using the descriptions from before. So for example, it might be inserting into the array. The additional commands are the possible commands that can run when I is in the set U. So that might be growing the array if it's full, for example. In the case of the dynamic array, there is only one additional command, which is to grow the array, for example. This additional command has the set U, let's say. There could, however, be more additional commands. For example, let's say every time the array has grown by a multiple of 1,000, the algorithm might sort the array, for example. There's just a function that we can implement. So this sorting command would be another additional command, and it might have its own set, let's say V. So when I is in the set U, the array grows. When I is in the set V, the array becomes sorted, and we perform an insertion on every value of I, regardless of what set it's in. So this might be an example of how we have the base command, so insertion, and two additional commands, which are growing the array and sorting the array. So calculating further, in the case of there being array growth and array sorting as possible commands, the algorithm would have one base command, so insertion, and two additional commands, array growth, which has set U, and array sorting, which has set v. There could potentially be any number of additional commands. So because in the previous slide we added a second additional command with set v. Each of which, so any number of additional commands, each of which has its own set. Just to let you know, I made up all of these terms. None of them are official. They do logically work, but if you're going to use them to answer questions, make sure you do briefly describe what they are. Otherwise, the TAs, being TAs, they are won't know what you're talking about. That said, they might not. If they're TAs, they might not even understand the descriptions either. But yeah, just to be safe, because nothing I'm saying is official. Let's take n as a number of base commands to execute. So let's say the number of insertions into the array. For every additional command that exists in the algorithm, we'll take a variable that states how many times each additional command occurs after, let's say, n base commands. So the two additional commands we have with sorting and growing. So let's say after n base commands, there have been j array sorts and let's say k array growths, if that makes sense. So if we know the value of n, then we can look at the algorithm or the code to logically calculate what j and k might be. Nearly done with calculating amortized complexities. Every additional command, it has its own set, so sets u and v, for example, the previous two, and they will also have their own variable. So in the previous slide, we introduced j and k for the number of sorts and the number of growths. N can be so the number of base commands to execute can be defined in terms of each variable. If we look at maybe a program's code or algorithmically, and the total number of times that every command runs after n base commands can be calculated. So as I said, it'll need to be done logically by analysing the code, or maybe it's given in the question, which would be very helpful. To calculate the amortized cost of the base command, find the sum of the total number of times that each command runs, so for code analysis or otherwise, then divide this by the total number of base commands executed. So we have all the variables, n, let's say j and k, for example, they are, and we can use those to calculate the total number of times that every command has been executed, and then we can as it says here, we can divide it by the total number of base commands executed. So let's say that we only have, let's take an example, we only have one additional command, which is growing the array. So let's not use sorting the array for now. So we can take n as the number of insertions, hence let's say k as the number of growths after n insertions. So n can be defined in terms of k, and so can the number of growths. So adding together, so k is the number of growths after n insertions. So we can define n in terms of k. So adding together the total number of insertions and the total number of growths gives the total number of commands to execute after n runs. And then, as it says in the second paragraph, we can divide this by the total number of base commands. So dividing the results of the sum of all commands by the number of base commands gives the amortized cost. It's like a kind of average. I know I said before it's similar to an average. It's similar to an average. It's not exactly an average, but I'll say it's similar. It's similar to an average of all commands over the number of base commands. So we have the sum of all commands over the number of base commands. So the amortized cost can then be put into a complexity notation, so into the average fraction, then it can be put into a complexity notation like big O, omega, theta, etc. to result in the amortized complexity. So this is the theory behind it all, the base and additional commands. Remember, if you're going to use them in a question, make sure you state what they are. And this is a way to calculate it. So the total number of commands over the number of base commands for some value of n, if that makes sense. It still is a little bit confusing, but this is being recorded, so of course you can come back to this slide however often you want. So let's move on from yes, base plus additional over base. That's correct. So let's move on from hell. Let's escape from amortized complexity, and let's go on to complexity methods. So how might we find complexities? So, showing that a program has a complexity. A program will always have complexity notations of all types, because there exists some mathematical function that the runtime will follow. So there are some typical steps and methods that can be followed to show that a program or an algorithm has certain complexities. So every mathematical expression has a complexity. So, for example, a polynomial might have a big O complexity of the polynomial's order, so highest index of the variable. So order 3, maybe n cubed, might be the optimal big O complexity. So every algorithm has a mathematical expression denoting how to use parameters. So in the second paragraph we say every mathematical expression has a complexity. Now we're saying every algorithm has a mathematical expression. So the parameters are arrays that have a particular amount of data. So the usual steps of finding an algorithm's complexity are analyzing the algorithm to find an expression. As we say in the third paragraph, every algorithm has an expression. And then we analyze the expression to find the complexity. So in the second paragraph, every mathematical expression has a complexity. So these are some steps that we can follow to find a complexity. So let's take an example. Here's where some sorting algorithms come in as well. So you can analyze the code of an algorithm to determine the number of operations performed on the data. Here's a recursive bubble sort algorithm. It sorts the array ascendingly by iteratively swapping to adjacent unordered elements. So as you can see here, via analysis, we can see that each recursion, so the third lowest line, we say if it's still unsorted, return bubble sort of the array. This is how we can do it recursively, not an example. So we can see that each recursion ensures that the next smallest integer starting with the largest is in the correct position, because if we're shifting through, if we're going through the array from, let's say, left to right, then of course when we find what should be the largest integer, it will continue being shifted until it reaches the end. And then if it's still unsorted, we return a new bubble sort of that array, which will again do the same thing with the next smallest integer from the largest. It will be shifted all the way to the right. So surely that means for n items, the recursion should theoretically happen n times, and this is just a recursion. And in the worst case scenario, each recursion should sort n minus previous recursions items, because if the previous recursions have sorted, in the worst case scenario, the number of items, a certain number of the largest items, then only the smallest ones still need to be sorted. So that's in the worst case scenario. We can draw this like a table. I haven't drawn the table, but if we were to draw it like a table of n recursions for n swaps each, then in the worst case scenario, the table would show that there are approximately n minus 1 squared over 2 swaps in total. I think that's right. I haven't drawn the table, as I say, but if I'm wrong, then I apologize. Yeah, but it's how it might be logically done. So n-1 because the swap requires it requires 2 items, so there'll be 1 less swap than the number of items themselves. So this is a polynomial of degree 2. This is an example of how we can find a mathematical expression from an algorithm. So let's try some shortcuts now. So there are some shortcuts that you can use. So previously with the bubble sorts, we analysed the code. It might take a bit of time for larger algorithms, but let's see if we can use some shortcuts. So for example, look at the number of nested loops that we go straight through. So here's an slightly inefficient, actually very inefficient, and flawed selection sort algorithm. So this sorts the array ascendingly by selecting the next largest integer and putting it in the next position. So as I say, it's very inefficient. So it has 1 for loop on the 4th line, and then after that for loop, it has 3 nested for loops. So there's a lone for loop near the top and 3 nested for loops. So one of the shortcuts we can use is see how many nested loops there are, because that would theoretically give a polynomial. So there are 3 nested for loops, which already generates a polynomial of degree 3. So of course these shortcuts are done by logical assumptions. Can you see the flaw in the code, by the way? It might not necessarily be in the code, but out of interest, do you guys want to think about what the flaw might be, or should I just move on? Next does work. It's it's called a label. So as we can see, the comment next to it where the break goes to. The flaw isn't itself. It isn't in the code itself, but I'll reveal it here. What might happen if we have 2 equal integers? So of course you might need to run through the code in your head, but actually it might take a while. Tell you what, you can come back to the recording if you want, because it might take a while to run through what happens. Let's see. I believe it would go straight to the return. So I tried it in IntelliJ, and it duplicates. So if there are 2 duplicate numbers, it ignores that duplicate and instead duplicates it duplicates the largest numbers in the array instead of the ones it should. So that's what the flaw would do. But yeah, if you want, you can come back to the recording and play around with it if you want. So so we've looked at how we analyze an algorithm of the code to find an expression. Now, let's take that expression and find the complexity from it. So usually when we look at an expression, we can accurately guess its complexity. So let's say 3n squared plus 4. It's in big order n squared, little order n cubed. It's in omega n squared, theta n squared, and it's tills with 3n squared. With big O, that uses the wizardry, doesn't it? Bloody constant. This is why I prefer little o. Sometimes, however, we want to show how an expression has a certain complexity. So a question might say, show that this complexity applies. So 2 typical methods of showing this are infinity limits and manipulating inequalities. I know that there are more methods, but these 2 are quite typically used. So we've seen how infinity limits work. So we can find the limit as n approaches infinity of f of n of g of n, and we can identify which of the three scenarios occurs, so whether the result is infinity, a constant, or 0. So this tells us whether or not g of n is a suitable complexity for f of n with a given notation. That said, with tills, it needs to be a constant, and the constant needs to be equal to 1. So, of course, there might be 4 scenarios, one of which is like a sub-scenario, if you want, of the constant. Yeah, excuse me. So, finding complexity. So infinity limits we've seen before. Manipulating inequalities is another way of doing it. It's like showing that an m and a c would exist. It does, however, mean that it can't be used for notations that are only defined with infinity limits, because, of course, they can't be. They can be defined in predicate, but it's slightly more difficult, I think. It's easier to define those in infinity limits. So manipulating inequalities can be used for anything that can be defined in predicate with m and c. So that's big O, omega, and theta. Let's say we have an f of n, so runtime, by analysing code, and we want to show that a certain g of n is suitable for a given notation. We know ourselves that the most significant term of f of n determines its complexity with big O, omega, and theta. If we're trying to show an inequality between f of n and cg of n, for theta we might have c2 g of n as well, because of course it has c1 and c2 for the upper and lower bounds. Well, for the coefficients of the bounds, then we have an inequality that we can actually change and manipulate a little bit. So we can change and manipulate f of n and g of n as long as the inequality becomes tighter. This might be a little bit tricky to conceptualize, but for example, by becoming tighter, let's say if f of n is less than or equal to cg of n, then if there exists something greater than f of n that still satisfies the inequality, then it's greater than f of n, so surely f of n will still satisfy the inequality. So this is what I mean by we can change and manipulate f of n as long and g of n as long as the inequality becomes tighter. So that there's a little bit of oh, hang on. So sorry, I didn't have that paragraph up. Okay, I'll through it again. By becoming tighter, for example, if f of n is less than or equal to c times g of n, then if something greater than f of n still satisfies the inequality, then f of n will still satisfy the inequality. So g of n can also be altered in the same way. So as long as it becomes tighter, if you can logically visualize it with which way the inequality is, then that will allow us to manipulate it in a certain way. So next, we can calculate an m. So in the third paragraph, we've provided a c that we know will work. So we can say any number for c. All that matters, as we learned from the predicate, is that it exists. It doesn't matter what it is. Just if it exists, then then it will work. We could use that for m. We could just state an m that happens to work, but sometimes the question will want us to calculate it. So you can rearrange and manipulate using mathematical rearrangements the inequality. However, you'd like to show that an inequality exists for n that satisfies whatever complexity notation we're given. So, excuse me. So, resulting in some n for which all n is greater than or equal to m from the inequality. The manipulation that we did before, so making the inequality tighter, simply makes it easier to find an m. So let's say if we have like a polynomial of degree 4 or something, it might take a while to find an m. What we can do is we can change the terms in the polynomials as long as the inequality becomes tighter, and then that might just make it easier for us to find an m. Remember, as long as some m exists, so manipulating f of n and g of n to make the inequality become tighter should make it easier to solve. Yes, so if we try it and we end up with like a polynomial of degree 6, we can think, okay, let's make the inequality a little bit tighter, because we know that the most significant term determines its complexity. So we can change any term as long as we're not changing the excuse me. Yeah, we can change any term as long as we're not changing the most significant term, because we know that an m is going to exist. So we can effectively make the inequality tighter, and then it makes it easier for us to find some kind of m. So, nearly done. So, multi-algorithm programs. So we've looked at too much stuff for me to count, but yeah. So final part: multi-algorithm programs. Programs with two possible functions. This is kind of what I at the beginning I said will be kind of the difference between the complexity of a program and the complexity of an algorithm. This kind of slots into it. So programs with two possible functions. Then so a program might have two algorithms which each executes if different values of n are in the input array, for example. So for example, if n is smaller than a certain value, the first algorithm might execute, whereas if n is greater than that value, then the second algorithm might execute. Of course, each of these two algorithms will have their own complexities, but does the program itself have an overall complexity? So the program contains the algorithms which have their own complexities. Are we able to use them to say the program itself, which contains the algorithms, has an overall complexity? So will f1 of n, will the f1 of n algorithm run, or will the f2 of n algorithm run? So we're taking n as the array size, f1 of n as the first algorithm's runtime, and f2 of n as the second algorithm's runtime. So we can assume that, let's say k is natural, and it's the value of n at which, when exceeded, the second algorithm runs instead of the first algorithm. So the f1 of n algorithm will run if n is less than or equal to k, and the second algorithm will run if n is greater than k, for example. So, hang on. Yeah. Should we use so the entire program, it contains both the f1 of n and f2 of n. Which one should we use when calculating the complexity of the program? As n tends to infinity, f1 of n over g of n and f2 of n over g of n will each converge to either infinity, 0, or a real constant, as the three scenarios from before, as for a complexity function. All complexity notations can be defined using the infinity limit of n. So big O, theta, and omega can be defined in predicate as well, but all 5 of them, including little o and tilde, can be defined in terms of infinity limits. So most of which f of n over g of n converges to infinity, a constant, or 0, or 1 for tilde notation. If f1 of n satisfies a complexity function whilst f2 of n doesn't, then it's possible for f1 to be of complexity g whilst f2 is not of complexity g for CPLX's complexity notation. So because all 5 complexity notations can be defined in terms of infinity limits, theoretically we should be able to use the infinity limit to show that whether f1 of n is of complexity g, and f2, same for f2 of n. Hang on, f1 of n only runs if n is less than or equal to k, and k is less than infinity. We're using infinity limits, but f1 of n can't run as n approaches infinity. This means whatever f1 of n over g of n converges to is irrelevant, theoretically. As n tends to infinity, the program discards f1 of n and uses f2 of n. So, n must be able to reach infinity. This is the case for any function where n is restricted by an upper limit. So, of course, there might exist some value of m for which f1 of n is acceptable as an upper bound, but then of course, when n becomes large enough, or it becomes greater than k, let's say, the program swaps to the f2 of n algorithm. So f1 of n, even if it's acceptable for some value of n, then it will be irrelevant because we can just choose a higher m, for example. No matter what the upper limit is, it also prevents n from reaching infinity. So this means that there will always exist a natural m greater than k, because k is fixed. K is the value at which the program swaps the algorithm it uses. So there will always exist a natural m greater than k, and we can choose whatever m we want. The only thing that matters is that it exists. So of course sometimes we'll need to calculate it like in the previous section, but the only thing that actually matters in terms of notation is that it exists. So in terms of the program's runtime, any function where n is restricted by an upper limit is irrelevant. So if n is restricted by an upper limit, then the function will be irrelevant because n cannot tend towards infinity. So we can just choose an m, choose a value of the natural m for which n is always small in the first function. The runtime of the program, the entire program, is equal to the runtime of any of the program's algorithms that can still run as n tends to infinity. So this is how we can use the runtime of its algorithms, the program's algorithms, to determine the entire program's runtime. So this, an interesting point is this also means that instead of having 2 functions, one of which is restricted by an upper bound, let's say if the f1n function runs when n is even and f2 of n runs when n is odd, neither algorithm will be restricted by an upper limit. So because of course there exist even numbers that tend to infinity, and there exist odd numbers that tend to infinity. So the runtime of the entire program should be, let's say with big O notation, or little o notation as well, the greater of the orders, so the runtime that we use should be the greater of the orders of f1 and f1 of n and f2 of n. So as long as n is able to reach infinity, then we can use that for the oh, I'm tired. Let's bring this to an end. You survived. Congratulations, and thank you for listening.